Okay, everybody. Section 1.3 is what Jean-Marc covered today, so I'm going to do a quick little review. So he talked about continuous and non-continuous functions. He used the roller coaster analogy, but basically a continuous function, the one on the right here, has no breaks in it. You can move your pencil along the entire line and nothing happens. Okay? We sometimes call that a well-behaved function. And to solve those types of limits, you solve just by plugging in whatever number you're going to because you have no undefined points. So for example, if I have the limit of 2x squared plus 1, we know that this is a quadratic. The only two cases where you have undefined points that we looked at in Math 12 was if you have a square root, because you cannot square root a negative number, you will have a domain restriction, or if you have variables in the denominator, neither of which occur in this parabola. This is a polynomial function. All polynomial functions are continuous. So if I wanted to know the limit of this, I just plug in 4, and I get 2 times 4 squared plus 1. 4 squared is 16. So I get 32 plus 1 is 33. And there you go. That's the limit. Nice and straightforward. The one on the right here is not a continuous function, and not a non-continuous function will have breaks. So if you're trying to follow it, you get to this point and there's a hole here. We called that a POD in Math 12. And remember, PODs occur when you have the same factors canceling. All right, or asymptotes like we have there, which is when you have a variable in the denominator, or you can have a piecewise function where there's a jump. There's a whole bunch of different cases, and we will look at those. We're not too concerned about the graphs right now. We're going to look at how you solve these functions analytically, i.e. using algebra to get the limit, okay? So there's a variety of techniques. There's 3 basic ones we're going to learn today. So let's look at our first example. If we have the limit as x goes to 1, x squared plus x plus, that doesn't matter, it can be 1, over x plus 1. All right, so right away we look at it, you might see this. We have a variable in the denominator, so that would mean that x cannot equal -1. But are we approaching -1? No, we are not. We are approaching +1. So even if there is a discontinuity, a gap, a hole, a vertical asymptote, a jump, whatever, as long as the function is continuous at the point you're going to, you can sub in. That is your default method. Always try subbing in. So in this case, I can just sub in x is equal to 1. And you get 1 squared plus 1 plus 1 over 1 plus 1, which gives me not 3 over 3, 3 over 2. And that's it. That's the limit. Nothing to it. If you can sub in, you sub in. That is your simplest and fastest way to do it. However, that's obviously not always the case. So if we have x going to -3, x squared plus x minus 6 over x plus 3. So obviously, if I plug in -3, I end up with something over 0, right? Because the denominator is undefined at x is equal to -3. So you can't do it. So you have to manipulate the function. And because this is a rational function, i.e. a polynomial over a polynomial, and if you were in my class, I'd always tell you, as soon as you see a polynomial and you don't know what to do, try factoring. So the numerator, what multiplies to -6 and adds to 1, so we get x plus 3, x minus 2, or x plus 3. And then clearly, x plus 3's cancel, and I'm left with the limit, so x goes to -3 of x minus 2. Now I can sub directly into that and get -3 minus 2, which is -5. So the limit as x goes to -3 of this function equals negative 5. All right. So that is if you have polynomials. You factor 99% of the time, one of the factors will cancel. If the other example that he gave is if you have radicals, so something like this. Clearly, if I put in x is equal to 0, I'm dividing by 0, the whole thing blows up. So what we do is we use the idea of difference of squares. And I think I showed my Math 12 class this when we were doing trig proofs. If you have, I have x minus 1, and I multiply by the conjugate, which is the same, except you are changing the sign. You create a difference of squares. So when you multiply this, you get x squared minus 1. Okay? That helps us with radicals because as soon as you square something, the square root will go away. So I look at this function, I go, all right, I'm going to multiply by the conjugate in the numerator. So that's going to be x plus 1. And instead of having a minus 1 here, I change it to plus 1. But what you do to the bottom, you must do to the top. Or what you do to the top, you must do to the bottom, because really we're multiplying by 1. So it's x plus 1 plus 1. The top then becomes root x plus 1 times root x plus 1 is just x plus 1. The square roots go away. Negative 1 times positive 1 is minus 1. Don't multiply out the bottom. Just leave it. So that it looks like this. And you'll see why in a sec here. So now you can see the 1s will disappear. And I'm left with the limit as x goes to 0 of x over x times root x plus 1 plus 1. Now you can see those x's cancel. I got 1 over root x plus 1 plus 1. Now it is defined because we removed the discontinuity at x is equal to 0, so I can plug that in. And I get 1 over the square root of 1 plus 1 is 1/2. Okay, so when you have a radical or square root, in this case, always use the rationalizing technique by using the conjugate, okay? All right, the third type, is when you have compounding fractions, i.e. a fraction over a fraction. So, whoops. The limit as x goes to 0, 1 over x plus 2 minus 1/2 over x. Clearly, if I plug in 0, the world's going to blow up because we have a 0 in the denominator here. So you need to make a common denominator. Common denominator, you're basically is going to be just munching the denominators of these two denominators together. So you can think of it as you're multiplying this one x plus 2 over x plus 2, and this one by 2 over 2. So we end up with the limit as x goes to 0 of 2 minus, please bracket whenever you're subtracting, 2 times x plus 2, and it's all over x. And just because this is calculus 12, usually things are rigged to work out. So I expand the top by dumping in the negative. Minus x minus 2 over x. So clearly the 2's are going to go away. I end up with negative x over 2 times x plus 2, and it's all over x. Now that's like over x over 1. So you're going to flip the denominator. And then you can see these x's cancel. The negative does not cancel. And I'm left with this. The reason this is good is we've removed the discontinuity that over x, the denominator of x is disappeared now, so that I can plug in x is equal to 0, and I get negative 1 over 2, 0 plus 2, which is negative 1/4. All right? So there's another one that he never really talked about, but I'm going to show you just because that is, what if you have, what example is this? 5. The limit as x goes to 1, that. Now, it's polynomial. If you remember the formula for factoring a perfect cube, which is x cubed minus 1, you can do it that way. But if you don't remember that, and you remember your math 12, you can do division, polynomial division. Now, this is a linear denominator, because clearly if I plug in 1, I'm ending up with 0 over 0, which is the world blows up. So we can divide this.
Hit the sun. Actually, there was one weekend they came up here and it was beautiful, and I had to do some marking, so I set up right here and I had like the sun right in my face.
Okay, sorry about that. So we can divide this. So if we do synthetic division, if you remember synthetic division, what makes the denominator equal to 0? 1 would be our a value, it goes on the outside. Inside, we put the coefficients, but remember, we have to have space holders. So we need a 0x squared and a 0x. So it's going to be 0, 0, and then negative 1 there. And in synthetic division, we bring down the 1. Multiply 1 times 1 is 1. Add, you're always adding. 1, 1, 1. 0 is our remainder. And if we're dividing a cubic by a linear, degree 1, we should get a quadratic. So this is x squared plus x plus 1. So what we can say is this equals the limit as x goes to 1 of x squared plus x plus 1. That is a continuous function. We have removed the discontinuity. So I can now plug in 1, and I get 1 squared plus 1 plus 1 is now 3. And that is the limit. So that's a technique to use if you have something that you can't factor, all right, and you have a linear denominator. You could use long division of polynomials. That would work as well. If you have any of those questions, please come see me. But the basic idea is if you can plug it in, that is always your go-to step. Then if you have something that has a discontinuity that you cannot plug in the number, i.e. polynomial over polynomial, a rational function, factor and cancel, remove the discontinuity, and then if you have a radical, multiply by the conjugate, both the numerator and the denominator. If you have compounding fractions, make a common denominator for the top part of it, this bit, and you'll know you're doing it right because things will cancel and the discontinuity will be removed. In this case, the x's cancel out. And the final one, which you probably won't see very often, but just so you know, if you go on in math, if it's a cubic or a quartic or whatever degree, you can always just use synthetic or long division. Synthetic if it's a linear denominator, to divide it out and rewrite it. Okay, and your practice questions for everybody are on page 67 if you didn't get them on the board. 19, 21, 41, 43, 47, 49, 51, 53, 55, and 57. Please practice this, even Math 100 students. I know you have slightly different questions. This is getting into the crux of what a limit is. All right, people, best of luck. Talk to you later.